Okay. Good evening, my dear student. So this is the second class on embedded system. So today we are going to discuss, mainly we will focus on interrupt. So let me tell first what is called interrupt, because in microcontroller, for control and power electronics application, this interrupt is a very important event. So if you remember the last class where I have configured the ADC, because once the analog value, it is reaching the particular channel of the ADC, it will, and once you are starting the conversion, that time one particular bit was there, which is remain as high. Until the conversion complete, another value should not, you should not allow the program to take some other value from the same channel, then it will give some garbage value. So for that, what I did, I took it as a condition, and with that I made one infinite loop. That means once the conversion started till it is ending, microcontroller will be in a halt. But this is not advisable. So when the conversion is taking place, maybe some event is occurring, but microcontroller is not able to divert there. It should not be. Even though there will be a change of task of the controller, but totally microcontroller should not be in a halt. That's not a good practice. This can be avoided using interrupt. So let me tell, I used to give this a simple example to the student to understand the interrupt properly. Say, suppose now I am teaching you embedded system. Suddenly at this time, suppose in my house, my section head entered. So what I will tell you? I will tell you, my dear student, my section head came. You just wait for some time. I will go and attend my section head. Then I will go there. I will discuss with him what is his query. I will talk to him. I will resolve his query. And once he left, then I will come to you and I will start from where I stopped. So the entering of my section head in my room is called interrupt. I have not, if when he entered inside, I have not halted. I give a pause to my current task and going there, executing that, and again coming here. In microcontroller also, this can be implemented using interrupt. Let us take another example. When I am taking the class, so that time my section head came. I went there. I was discussing with him, resolving his query. While I was resolving his query, suddenly my director entered in my room. That time what I will tell my section head, please sir, excuse me, you take your seat here. Just I will talk to my director. Then I will talk to my director. I will resolve his query. Then I will send him off. Then again I will come to my section head. Where I stop to discuss, from there I will start and resolve his query. And then I will come to you. This example is called the priority of interrupt. When at a time, several interrupt event occurred, which can be taken first. That is based on your requirement. Which can be done first? The sequence, the priority. It's called priority of interrupt. That is also very, very important. And that in a microcontroller, there are several interrupts already defined. And among them, which one is to be executed first, that also you can set using some particular register. So we are going to learn it now, today. Basically, this interrupt we will be learning basically for one special purpose, which is called quadrature pulse counting. Normally, today, there is a optical device called shaft incremental encoder, which is extensively used basically in motor control or rotating machinery to predict its RPM. So in that device, there will be two square pulses, which will be aparted by 90 degree. 90 degree means 1/4 of 360. That's why it's called quadrature. Okay. So this, by counting this quadrature pulse, you can predict the RPM of the rotating shaft. So basically for that, we should learn this interrupt, and not only this, to generate the PWM, and so many huge other applications are also there. So first, we will discuss a very, very simple program. Say, in a particular pin, some pulses are coming. So how to count the pulse? Either you have to see how many times the pulse become high, or how many times it is from low to high transition is happening. Low to high transition, it's called raising edge naturally, and high to low, that is called the falling edge. So if we are able to count the raising edge or falling edge, then I can find how many pulse is elapsed. So basically that encoder will be giving the number of pulses per rotation, which is called PPR, pulse per revolution. If you, by detecting the raising edge, if we are able to count the number of raising edge and how much time taken to elapse certain number of pulses, then we can find out, because the number of pulses per rotation is given. So from there you can find out the speed of the shaft. So this we will be first, these things when we are connecting the external pulse to a particular pin of microcontroller, and we are configuring it as external hardware interrupt, you can detect the raising edge or falling edge or high or low, and by this way you can able to count the frequency also, frequency of the pulse or number of pulse. All these things it can be done. Hope my screen is visible to you all. My screen is visible?
Yes, sir. Visible, sir.
Okay. So already these are the things are not required. Already I have discussed the fundamental structure of the program. Here I have used one user-defined function to initialize the interrupt.
Yes, sir.
So that I will explain. And these things, because I will be watching this, I will be getting the value output of the program in the serial port. So that's why I am initializing the serial communication. In the external hardware interrupt initialization, I have used 3 registers. First register is SREG, one special register, status register. Here the 7th bit I made as high. Why we have done this? So let us find out what is this SREG. You see, this is the status register. And what I did the 7th bit or the ith bit high. What is that? Let us understand. So the 7th bit, you see, it is called global interrupt enable. Okay. So once you want to enable the interrupt, then definitely this bit is to be high. First job is to make this bit as high, which is called global interrupt enable. So as I am using some interrupt, so definitely my global interrupt bit is to be enabled, and that's why the 7th bit of the status register I made as high. Then I have used another register called EICRA. In this, if you see the code, I have used the first 2 LSB and made it as 10. What is this 10? This is the table. This table 12.1 is defining that. 10 means, you see, this is the interrupt 1 falling edge detection. So once in that particular interrupt 1 pin, any falling edge is coming, then the interrupt will be generated. Okay. So it will detect the falling edge. Okay. So that's why I made that 2 bit as 10. It's very clear. Then I have used EIMSK. And here you see, if I want to detect the raising edge, that particular 2 bits should be 1, 1. Okay. So another register, let us see what is that. EIMSK. You see, this is the EIMSK. And in the EIMSK, I have used the LSB as high. So basically, we are using interrupt 0. So to enable that one, you see, this is the external interrupt request 0, interrupt 0 is enabled. So we are connecting the pulse with interrupt 0. So that's why it is to be enabled. Okay. Then this is the service routine. ISR means interrupt service routine. It is a standard syntax of that particular ID. And all the interrupt, it is written in the memory as a vector. So that's why that standard syntax is interrupt 0 underscore vector. So if we initialize the interrupt 0 as falling edge detection, then once falling edge will be detected, microcontroller, it will generate one interrupt and it will be redirected to this service routine. So if in this service routine, what will happen? What instruction I have given? I have given to increment a counter, and that I am printing in the while one loop. This is a simple code. So let us see how this is happening. Now, if you see the code, what I have done, you see this pin number 2, it is written as interrupt 0. So I have connected there a push button. So once I press the push button, so what will happen? Normally it is grounded through this register. So it is in 0. So once I press the push button, from 0 to high, it will happen. Okay. But I have configured is for it for falling edge. Now here you see the value which is displaying, it is as 0. Now I am pressing the push button. If I press the push button, interrupt will, that particular pin will see a raising edge. Then also this value will not change. You see, I am pressing, nothing changing. Now if I release, now this pin will see one falling edge. And that time, you see that there will be an increment. You see, I released it, there is a increment. Further, I am pressing, no change. I am releasing, you see, it is increasing. So that means I am successfully able to configure interrupt 0 pin as falling edge detector. You see, I am pressing, and when releasing, if I press, no change. If I release, then only increment is happening. So now that particular pin is configured for falling edge detection. Now let us see how to detect the raising edge. So as I told in the table 12.1, to make this, I have to set it as 1, 1. And now if I run, you see, once I press, you see, it is increased. Now I release, no increment. Again, I am pressing, then only it is increasing. Release, no increase. Again pressing, increasing. So now that means this particular pin is configured for falling edge detection. So now we already learned. So end of this code, what we learned? We learned what is called interrupt, where interrupt is to be used, why it is to be used. There are several interrupts. during PWM generation, there will be some interrupt. I will tell you whenever that is required. And why interrupt is important. Using interrupt, we can increase the efficiency of the coding. Otherwise, sometimes we have to put pause. That we'll see in the next code. Now, if you remember the ADC code last time, whatever we discussed, all these things are same only. Everything is same. But here, few bits I have added. Here, few things I added. All are same only. In AD marks, I have used 0x41 because if you see that here I converted into hex. Hex means that's why it is written as 0x. If it is binary, it is 0b. So AD marks configuration, you can see in the, see my lecture on the, see my first lecture. There I have explained how we configured this AD marks. Mainly the last 4 LSB, it is used to select the channel. This AD prescaler bit I told already why this prescaler is required. And this status register, why is to be configured? Because here also you see the 7th bit is configured. That means we are going to use some interrupt. So once any interrupt is we are going to use, we have to enable the global interrupt bit. Now you see in ADC SRA, ADIE 1 bit I enabled. What is this things? We will see. You see, this is the ADC SRA. So in the ADC SRA, I have used ADIE bit. Where is this ADIE? 3rd bit. So what is that 3rd bit? You see, this is the 3rd bit. When this bit is written to 1 and the ith bit in the status register is set, then the ADC conversion complete interrupt is activated. You need not to put any hold. Once ADC completed its conversion, the interrupt will be generated and you can extract the value from there. You need not to put your microcontroller on any hold. It's a good thing. As I told, we are not putting hold in the microcontroller. So that's why the ADIE bit of ADC SRA I made as high. Now these are the 2 bits already I have discussed in the last lecture. This one is ADC enable, and to start the conversion, definitely you have to enable the start conversion bit. And now this service routine, because here we have enabled the ADC conversion interrupt, and once the conversion is completed, then it will be redirected to this subroutine. As I told, the ADC value after conversion, because it's a 10-bit ADC. So our microcontroller is 8-bit. So all the registers will be here as 8-bit, but the resolution of the ADC is 10-bit. So it is splitted into two, ADC-L and ADC-H. ADC-L, there will be 8-bit. ADC-L, there will be, ADC-L, there will be 8-bit. ADC-H, there will be 2-bit. These are the 10-bit configuration. Now you see here, first in ADMarks, this is the 0. This means if you convert into binary, it will be 0100 0001. So the last 4 bits, it is defining the channel number. Okay, and here I have used the switch case statement. So at first, what will happen? The value is already 41. So it will come to here. So once ADC conversion completed, then it will be redirected to this subroutine. Inside the subroutine, that index of the switch case statement is already 41. Then it will come here. It will print the value of the ADC. And after that, it is changing the channel number to 5 and breaking that case. And once it is 5, now ADMarks value is, the index value is 45, hex 45, and now it will come here. It will print the value. And again, I am making that value as 41. Then it is again going here. So like that, if there are several channels, you can make it case 41, case 42, case 44, case 45, like that. Okay. And after that, because again, you need to, after that, again, you start the conversion. One conversion is over, it is switching to this interrupt. So if you not write this bit, then the next conversion will not start. Because this service routine will be executed every time after the conversion of the ADC is completed. So after each and every execution of this subroutine, again you need to start the ADC conversion. So that's why I written this bit. Very simple. This code is an efficient code. There will be no such problem. Microcontroller will be not in hold. Okay. Now you see here, I have written there 41 and 45. So that's why the potentiometer is connected to channel 1 and channel 5. Okay. So let us compile the code, generate the hex file. You see, now I am increasing the value of channel 1. You see, it is getting increased. Okay. I'm reducing. The channel 1 value is getting reduced. I am increasing channel 5. You see, it is getting increased. So the ADC configuration is fine. Now I am reducing. It is getting reduced. So this is the application of an interrupt where we used ADC conversion complete interrupt. And it is a very, very efficient technique to configure the ADC. Okay. So this was all about, because I don't want to put in you a mesh, so that today I am telling all the things so that you may forget or you become bored, so that you're not able to capture it. But I want, because, just now I am very tired. I am just coming from my lab directly and I was waiting for you. So that my purpose is just you should learn and you should be doing that. It's not just like that your academics is completed. Or maybe some people will be there. Most of the people, they will be interested just reading to carry the marks. It's okay. You need good marks, but parallelly, you should be able to, because this all we are engineer, we should do something. We should be able to implement the things which we are reading. It should not be limited in the books and papers. That is my target. So these two things, anyway, it will be, I have recorded it. I will be sharing the link to Sir. Sir will put that link to your groups. You can see also. With this conception, the next lecture, we will be discussing about the PWM. It's a very important for power electronics and control. Okay. So there also we will be using one special interrupt, which is called timer overflow interrupt. Timer means basically what? Our clock. Our clock is a timer. It is counting 0 to 12, 0 to 12, again counting. So it is 0, 1, 2, 3, like that, going 12, again it is coming 0. This is a clock doing. So what is called the overflow interrupt? Means once it is started from 0 and again counting is completed, 12 till 12, again new counting is started. So once full counting is over, overflow occurred, means your one count completed. So this is called overflow interrupt. So microcontroller is, the inbuilt feature is there. Then if you can configure a timer and that particular interrupt is enabled, then every full counting is over, it will generate an interrupt which is called timer overflow interrupt. And using that is very important to generate sine PWM. So these are sine PWM is a very important feature in electrical engineering. You can, whenever you want to make your inverter, any kind of converters, variable frequency drives, all these things, it will be done through PWM only. So in the next lecture, first we will learn the fixed duty PWM with dead time generation. Then we'll be discussing about sine PWM with dead time generation. So after that third lecture, basically the basic things, it will be over. With this, if you really learn this, number one, you can do any power, you can play with power electronics component, you can make your own DC to DC chopper, SMPS, UPS, inverter, thyristor control. If you conceptualize this, using that, you can do that. Or further, if you are interested, I will continue few lecture on the practical implementation or particular case studies, like how to count the quadrature pulse, how to fire a thyristor, how to implement the code for MPPT, how to write a code to control a BLDC motor or induction motor. That I will decide based on your interest after the third lecture. So this was all about today's lecture. If you have any question, you can ask me. Otherwise, I will terminate the session. Thank you so much. Thanks for your patience. Anyone have any question, or I can terminate the session?
Yes, sir.
Okay, I can terminate the session.
Yes, yes.
Yes.
Okay, thank you so much. So we'll be meeting tomorrow with the next series of next lecture series. Okay, thank you so much.
Thank you. Thank you, sir. Good night, sir.
Thank you.